terms of the volume here. The volume of the slab, or the volume of this slice, we'll just make a note, is this surface area times dr. So I'm doing deriving here now, which I always don't like to do all the time because it makes things look V slice dr dt.
Sorry, what was J again?
Current density. In which I'm just basically saying the currents are the same, the current per area is the same, and we could express the current area in terms of this stuff. So this whole thing here is some sort of a constant, all other things being equal. I hope I'm not going around in circles here, but we'll see if I am. So if we rearrange this then, what are we left with? I'm going to bring the dr up on top. And now I've got a quantity that looks like dq over v slice times dr dt. And what is this? Well, dq over v, for a constant charge movement over this region, we can rewrite this as n charge carriers, if you will, per unit volume, times v. This is where it comes from. We'll think about this carefully. I'm sure I can do something. This is v. This is dr dt. So this is the functional velocity of the moving charge. Across this little slab dr. Okay, so you're following? I'm not trying to make this too esoteric, but I'm trying to sort of follow the logic where it comes from, rather than just do the equation.
Yeah.
The equation's the easy part. Figuring out the pieces of the relation. Yes. So what we're left with then is for a given charge density, charge density, charge per unit area, current density, excuse me. It should be related to the number of charge carriers per unit volume. And this is unit volume. This is not voltage. Times V. Now, the textbook might say something like this. Oh, I'm leaving one little thing out here. It's dq over v, so I got to put one other little factor in here, my mistake. This is the charge that's represented by this volume. Put it on the wrong side here. So I need charge density times each individual charge. Kind of like saying mass times atomic density would be the mass density. So this is number of atoms. This is electron per atom. Or this is a number of charge carriers. This is the charge per carrier. Okay, so I'm not trying to make that confusing. So be sure to put that little piece in here. We need to know the magnitude of the charge. Does that make sense to you? Just at any point stop me, I'll summarize once I get all this together. So here's where we're basically at. We should have a constant, uniform, it doesn't even have to necessarily be uniform throughout the cross-section, but for a constant current density, there's a relationship between the charge carrier, charge per unit volume, that's flowing, and the speed at which it's flowing. So, again, I'm going to remind you one other thing. This also corresponds to I over the cross-sectional area of the slab. Okay? So, three things we take away from this. First of all, for a uniform cross-section, we're going to have the same charge density at either end. Or current density, excuse me. For a particular material, we're going to have a uniform charge carrier density. And when you look at it in pieces, note something here. As the current increases, and by the way, this would increase by increasing voltage, if you will. As the current increases, it's linear to the voltage, to the velocity, the average velocity, or the drift velocity of the moving charge himself. So certainly increasing the current by increasing the potential difference, by increasing the electric force that's driving them through, you do get faster current flow. It's not a constant overall current and all voltage per se, but it is constant in the sense that for a given flow of current through a given cross-sectional area, you can calculate what the average net movement speed is of the charge. So this would be where we would go with this. Now, how do we then apply the calculations? We did some of the stuff up front. So now the question might be, well, what is V? Let's figure out what V should be. So first of all, I'm going to re-express it so you can see it in the least seeable color, of course. We should say the V then, speed, should be related to the current flow divided by the surface area. There's your J. I'm going to write it in long term, not in short term, or in long form. This stuff here divided by the charge of the moving carrier, which would be an electron charge, whether it's positive or negative. It's just E value, 1.6 times 10 to the negative 19 coulombs, times the charge carrier density, which is a constant for a particular material, for a particular density of substance. So I would highlight this. This is the drift velocity relationship. Or drift speed. Okay. Let's get rid of this stuff for a moment. So having gone through all of that, what are the pieces? Well, it has to do with the arrangements of the charge and how they're packed in there. It's certainly related to the potential difference you drive across it and the amount of charge that's physically flowing. So now we'll just say, so how fast does, well, we'll keep it simple, 1 ampere of current. And we'll have this drift through a 1 millimeter diameter. Why?
Ideal size wire.
Yeah.
Does resistance physically slow down the drift speed?
But that's built into I.
Okay.
So to this end, we might even start here and now do a couple different problems, different ways, and start to see different ways that it can go. So, set up this calculation, and the numbers look kind of nasty until you get to the final answer. But if we were to solve for V, we would take the current per unit area, and the cross-sectional area, if this is A, it's going to have a diameter of a 1/2 millimeter, or I mean a radius of a 1/2 millimeter. So the area of this thing would be pi times 0.5 times 10 to the negative third, or 5 times 10 to the negative fourth squared meters. And so we have 1 ampere divided by 0.25 times 10 to the negative 6 times 3.14, so 1.6 times 10 to the negative 7? 1.55. That even close in the ballpark?
Of your pi r squared?
Yeah. Oh, no, 0.25, not 0.5, 0.25 times pi, so that wouldn't be that. It would be less than that, it would be half of that, so negative 8, maybe 7?
Maybe 7.
Maybe 7.
Seven.
So 0.25 times 3 is, what, about 7?
Yeah, 7.5 times 10 to the negative 7.
That's what I've got, yeah.
Okay. Close.
Good try, good attempt.
Yeah, it's Tuesday morning, it's my Monday. And we divide all of this by all this crud we just calculated. And that crud would be 8.8, well, we got 1.6, I'm gonna say 1.6, I'm gonna do those decimal places, times 10 to the negative 19th coulombs, times 8.85, times 10 to the 28th free electrons. And I'm just going to write it electrons per volume. I don't know how to do this differently. Electrons per meter cubed.
What are we doing for our volume?
We already calculated the ratio
Oh, okay.
of volume of charge per unit volume. That was the key because it's a constant quantity, so we don't have to get too lost in a particular volume, but we could. So, okay, we got stuff here. So we've got 10 times 10 to the negative 12, so 1 times 10 to the 11 times 8.5. 8.5 times 10 to the 7? No. 7?
I got 9.4 times 10 to the negative 43.
No.
Got 9.35 times 10.
So we got 10 to the negative 19th and 10 to the negative 7th. They're both on the same side of the denominator, both denominator terms. And this is 10 to the negative 26th, and we've got 10 to the 28th. So that's 10 to the negative 2, and then we divide by some other stuff there, negative 4. And it's going to be somewhere around 10 to the negative 4.
Negative 5.
You gotta do 9.3 times 10 to the
1 times 10 to the negative 4. There you go. So 9.35?
7.35.
10 to the minus 5.
and the units would be meters, because these go away. Charge per second. I should probably, that is charge, where's my seconds at? Oh, right there, coulombs per second. Everything cancels out except for meters per second. What's that?
That's damn slow.
Damn slow. Now, by the way, there's a couple of subtleties here, and this will, I don't know if it really necessarily matters or not, but yeah, it's about a 10 micrometer, or 0.1 millimeters per second, I guess. Think about how long it would take to cross 6-inch wire, 10-centimeter wire. It's a long time.
So, to extend this question then,
And this is in the direction of I, by the way. Right, the direction of I is the direction of the movement.
so when you're sending information through a telephone wire or something like that, the only way that that information can travel as fast as it does is if it's changes in current flow that's traveling. Yeah.
Absolutely. All of a sudden it changes your perspective on everything.
So that's the 1 and 0.
Well, yeah, this isn't very fast, but because this happens so fast, so fast in, fast out, slow in, slow out,
Right.
sinusoidal, what have you, or burst in, burst out if it's digital.
Yeah, if I smack an electron on one end, all the way on the other end, almost instantaneously, an electron pops out. So if I change the rate at which I'm cramming these electrons in, then I can have some kind of instantaneous, I can talk to my dad on Skype in South Korea in real time.
Think about it, think about it like a sausage maker. Put all
Right.
that meat in the front and you're grinding it and it's coming out, and if you push it in faster, then it's gonna make it come out faster the other end. And
Yeah,
you slow it down, it'll come out slower, and you control it if you're gonna twist the ends off. And we had a great sausage making class there. It's a continuing it, or community class. Kind of cool. Did that for the first time last quarter.
You eat sausage in class?
What's that? No, I didn't do it in class. I took class, yeah.
You took a class last quarter?
Yeah, in sausage making.
did you roll the sausage down an inclined plane and measure the rotational velocity?
I did not, but I thought about it. Unfortunately, it also corresponded to it being brought to my attention that minimizing any form of sausage reference in class would probably be to my professional betterment.
Okay.
So, nonetheless, you can kind of get a sense of this.
Yeah.
So, that's my justification for why it's so slow. But note, again, that is like 8 orders of magnitude slower than just the random movement that's happening as these things are just vibrating along. Yeah, it's tiny. That's why they call it a drift. And if somebody is doing the Brownian motion paper, understand that things are not just a forward thing. You've got Einstein's paper, you've got these things and they're kind of doing this, and on average they're kind of moving forward a little bit. Because they do have all this other motion. And that motion is random. It's thermally driven. Okay, so this is kind of a long chain of events though. I mean, this is, I think, a rather in the big scheme of things, it's probably least technically interesting because we kind of want to go right to electric charge or currents and electrical circuits and whatnot. So maybe it's a little bit less engineering interesting, but at the same time, there's a lot of stuff here. This is not an easy thing to sort of think through and think about. And I'm probably not as eloquent as my physics professor was when I took this subject, but it was basically this description and a description of resistivity in Ohm's law that basically was my final transition point to go into physics instead of engineering, was actually thinking about the pieces involved and not just V equals IR, now just solve a problem. So we all have our different things. This was sort of my turning point. Okay, so let's take a break, and when we come back, we'll sort of fill in some pieces to this, and hopefully get it related to electric circuits where we need to be. In a average, in a particular orientation direction. Yes, absolutely. But it's the perfect example of where you take a magnitude and an angle, actually be two angles. You'd have an azimuthal and a polar angle. And having it split into an X, Y, and Z pure component, as opposed to taking something that's moving this way and saying, oh, well, we can break it into X, Y, and Z. Now it's purely an X, Y, and Z. And then you can calculate the equivalent magnitude and direction, but they are physically independent. So there's some cool stuff here. And the applied math and the assumptions from going all the way back even to like chapter 2 start coming into play a little bit in a different way. So you think about having a three-dimensional lattice that you could form, that you can drive charge or even magnetic memory information. You think about, oh, gee, adding that extra dimension could just totally increase capacity of information. Okay, so now let's go and take a brief moment and go back to. So that's basically how charge moves. That's functionally the mechanism of how the electric charge moves. Now, coming all the way back to basics, and this relates all the way through all of this stuff, we can say that the current flow is directly proportional to the potential difference between the endpoints. Okay, this is just like a hillside, if you will. So, I'm going to draw it over here. Actually, I've already got a drawing, so why reinvent the wheel? So we have same sort of conductor here. And in fact, I'm going to make this a rectangular conductor because there's all kinds of stuff we can take from this. So we've got a rectangular prism conductor, and it's going to have a potential difference between the endpoints, delta V, and a certain length, L, a certain cross-sectional area, A, and the movement of charge, well, electrons this way, current this way. Reminder, it flows backwards, so don't, it's an easy one to forget, especially when you're in a hurry. And just sort of heuristically, a few things that we can say about it. And this comes all the way back to charge carriers. Is that the broader the cross-sectional area, the more on any particular slab or layer as you move along, the more charge that's available to physically pop out one end as you pop one in on the other side. And now this is the context. It wasn't so obvious when we were talking about it on Friday. The context of it is very much that. So you've got more available free electrons to push out on any one successive plane if you move along. So the greater the surface area of the cross-section, which is the A, and it's inversely related to length. Because for all of this stuff, you got to physically push it along against the ability of each electron to basically get sucked in to the next atom, to every other atom that's in front of it. And I'm going to put a constant down here in a very curious place. Normally we put proportionality constants on top. But I'm going to put a constant down here. And this constant, well, conductivity would go on top. The resistivity goes down below. But since we typically deal in terms of and resistivities, might as well just start there. So we kind of minimize additional confusion. So this resistivity property is basically intrinsic to a material. So carbon, copper, any particular material will have a certain resistivity property. And it would be an empirical fudge factor that an engineer would measure. Or at least determine in terms of the proportionality of all this other stuff. Now, if you just sort of rearrange this, so this is sort of the heuristic argument, but if you rearrange this, we might just note that if I rearrange it in such a way that I look at the proportion of potential difference to the amount of charge flow that passes through a conductor at that potential difference. This quantity should be related to this resistivity times the length of the conducting pathway, and inversely related to this area. This ratio, which is basically population is what's flowing. There's your current. The driving force is your potential difference. But the ratio of driving force to the population of movement, or the rate of movement, is what we call the resistance. So we give it a constant, we call it resistance. And the units of resistance are volts per ampere, or write it as a sigma, or sigma, an ohm. Is it sigma? It's not a sigma, it's omega. Omega. So this basic relationship, and here's, to get a sense of it, A we assume is a constant for a particular pathway, a conductor. L is constant. And so the only thing that we have in here that is not purely constant and dimensional is this idea of resistivity. When resistivity is constant, everything in this product quotient is a constant quantity. When it's not, this quantity is not constant, implying that R is not necessarily constant. So if the ratio of V to I is constant, it implies a constant rho. When it isn't, then you have a variable rho, or a variable resistance. So, in general, this relationship is what we call Ohm's law. And a couple things that we'll take away from it. There's more than one note here. First of all, intrinsic physical properties. Think about the ones we've talked about so far. Give me an example of an intrinsic physical property. We've already written some down here. What's an intrinsic physical property? First of all, what does it mean? It's substance independent, or I mean substance dependent. Doesn't matter the size, doesn't matter the shape, it's substance purely dependent. So a particular substance has this particular quality. That's an intrinsic property. So what's an intrinsic property we've dealt with? Just today?
Density.
Density. What else? Close to texture, and I'll refine it. Emissivity. Pretty close to intrinsic. What's another one? We talked about it